Hi, everybody. I thought I would do a very short video going through the key ideas in Chapter 10. I think it's very important for you to read Chapter 10. As you can see, Chapter 10 is a recapitulation of and practical tips for regression analysis. We'll spend some time reviewing regression analysis and then at the end of the chapter, look at an actual paper published in economic history and economics, and then in class on Thursday we'll talk about some other papers and their regression analyses. So it's a chance for us to practice regression analysis. So let's get started. The first point to note is this is our general multivariable regression model. Our outcome y is a function of several explanatory variables, x1, x2, all the way up to xk, and we have an error term that is due to other factors that are affecting the y or measurement error. The specification of this multiple variable regression model can be complex. We could have log specifications, log linear, log log, linear log. We could have polynomials. We could have dummy variables. We could have interaction terms. So all those things could be in this general model. Um, in this model, the beta are the parameters that describe how a change in the associated explanatory variables affects the outcome. Again, these betas can be complex in the sense that if we have nonlinear relationships, the no, not a single parameter describes the relationship. Instead, maybe two parameters, the coefficient on the main term and then the coefficient on the squared term, explain the parameters. There may be an interaction term, so then another coefficient is needed to explain the relationship between the main explanatory variable of interest and the outcome. So these betas can be complex in terms of how we interpret the relationship that we're estimating. Every beta will have a standard error, so we'll recognize that the sample is one of many samples that could be drawn. So our estimate of the relationship of these parameters, beta 1, beta 2, beta 3, beta k, that we estimate should be seen as random variables. They'll have variation, and our estimate uh, of the variation itself we'll call the standard error of beta 1k, which then allows us to conduct hypothesis tests. So let's continue on down. This is all straightforward review. Some of the variables are indeed dummy variables. We could have dummy variable as the outcome variable, and that, remember, that's the linear probability variable. We interpret the coefficients as being the change in the probability of being the one category. So a little bit of recap. That was from before the midterm, but we could certainly see that again. Um, so interpretation of the coefficients is something that we're always interested in, right? Nothing new here, but good to read it and see how it's written and try and write down. In fact, the good exercise is try and write down from memory pretty much this whole chapter, and that tells you how much you've absorbed over the course of the quarter. Um, our next section reviews how much confidence we have in these estimated coefficients. That is the question of inference or statistical significance. And the way we're doing that is a straightforward, simple way in this class, Econ 41, which is to conduct hypothesis tests. So we say that there's a null hypothesis, and our null hypothesis is the same for all our estimated coefficients, which is that the coefficients equal to zero. And then we calculate a t-statistic, and the t-statistic is the difference between the t-statistic is the difference between our estimated coefficient, our null hypothesis divided by the standard error. Because the estimated coefficient by the central limit theorem follows the normal distribution, the t-statistic follows the standard normal distribution. And thus, we can conduct hypothesis tests whether uh, if, if our assumption is true that the coefficient's equal to zero, what's the probability that we would observe a t-statistic or coefficient so far away from zero as what we observe. And so we can calculate that probability. That's the p-value, and our convention is that we'll say that the coefficient's statistically significant if the p-value is less than 0.05. If the probability of finding such a large coefficient so far away from zero is less than 5%, we'll say, well, that's pretty unusual, so we should reject our null hypothesis that the coefficient's equal to zero. Um, that's again all review, but it's useful for you to read through it again. Um, the the t-statistic itself, I think right here, I think these are important things to note, and you should study that. We haven't talked too much about the formula for the standard error, but the standard error depends on the sample size, the overall explanatory power of the regression. So the standard error will be smaller if the R square is larger or the adjusted R square is larger. The standard error of an estimated coefficient also depends on the degree of variation of the exogenous variable, of the explanatory variable. And then it also depends on the correlation of the explanatory variable with the other explanatory variables in the multiple variable regression case. So we see that we have a number of things that determine the standard error of any coefficient, and hence whether we're going to accept or reject the null hypothesis that the coefficient's equal to zero. Um, Another important aside here, or digression, is that the goal of regression analysis is not to have higher R squares, not to just increase the R square. That's why we introduced the concept of the adjusted R square, to penalize you in terms of goodness of fit by having too many explanatory variables. Some people call that overfitting the model. So that's penalized in the adjusted R square, but R square is not the goal. The goal is to estimate the magnitude and statistical significance of the parameter of interest. You're interested in a relationship, so you're interested in how the main X variable that you're interested in affects the Y variable. It might be a nonlinear relationship, in that case it's more complex, but you're interested in that, not in the R square of the regression or the overall explanatory power. So important point to remember, certainly one that every student of econometrics should be clear about. I also have here some language that I think I've mentioned many times during the course of the course, and I'd love for you to pay attention to this language, not use words like this regression proves this or that, but always a more modest interpretation of what your regression findings are. That is, they suggest an association between the X and the Y of this magnitude, or rejecting the null hypothesis that it's equal to zero. So let's continue on down here. We have section about interpreting the coefficients of regression. And I'm not going to say too much about this except to remember to calculate, to know how to calculate. Let me get my pen here. Know how to calculate standardized coefficients, how much a one standard deviation in the X variable affects the Y variable in terms of standard deviations of the Y variable. So standardized coefficients are comparable across different variables in terms of their effects on the outcome. Give you some examples here about interpreting coefficients. Remember that we can always rescale explanatory variables. If we have population, a one person increase in a population is not going to be have a very large effect on anything, but a 1 million person increase in population of a state or a country is the magnitude of the change. So we might rescale our population variable to be population in millions. So again, sort of this section here, which I encourage you to read and think about carefully. Let's continue down. So interpreting coefficients, I do have a interpretation here of proportions and percent kind of variables in a regression equation. So I want to encourage you to read that pretty carefully. And let's see, more discussion of proportion percent, some box about interpreting coefficients and more complex model specifications, log specifications, dummy variables in the specification. So this is a good box. It didn't render quite right. I will clean this up tomorrow. It should be a little clearer. This has to be deleted. I'll take care of that tomorrow. And then finally, we have our goodness of fit measures, which you're very familiar with, the adjusted R square and the R square and the standard error of the regression, and talk here a little bit about the idea of parsimony and have nice little excerpt from a lecture notes from the 1960s where it's talking about being parsimonious in your model selection. So I thought that was nice. Encourage you to read that. And then we come to an example of a regression equation, this regression equation by Nathan Nunn. I'll make a separate video about this, to go into a little bit more detail about this. And then I think that's it for this chapter. So I encourage you to read the chapter very carefully and watch the video about this regression, the relationship between slave exports and income of Nathan Nunn. So hope that was a good introduction to the chapter, which I encourage you again to sit down and read carefully.